Welcome again to this course on CFD. Today we are on module 4 of this week. So far we have seen direct methods in detail. Today we are going to see a new procedure, what is known as iterative methods. Any linear system can be solved by Gauss elimination or LU decomposition procedure. The question is, if the matrix becomes complicated, whether the Gauss elimination or LU decomposition procedure is economical or whether it will lead to some erroneous solution. In such situation, what do we do? The second question, whether it is computationally or in terms of time wise economical to do direct methods, or is there a way that we can go by iterative way we can get the solution. There are other issues. For example, triangular factors of a sparse matrix. So, sparse matrix is you are not able to identify matrix into some form, it has elements distributed throughout, it has values distributed here and there in the particular coefficient matrix. Such matrix is called sparse matrix, and triangular factorization of the sparse matrix is usually very expensive. While solving, we have either error due to computer arithmetic, handling of numbers, rounding off error, or there is also error due to discretization, and discretization errors are usually much higher when compared to machine rounding off error. We should have method which is more accurate than discretization error, and iterative methods provides a suitable alternative, and it is also good for problems involving nonlinear. So, it is suitable for nonlinear problems. In iterative methods, one initially makes a guess of the solution, then progressively improve and get the accurate solution. Each iteration is less expensive, number of iterations required will happen to be small, hence overall computational time requirement is also less when compared to direct method. So, we start with the initial guess, that is x at 0, then substitute into the right hand side of all the equation, generate new approximation value, and we call that x of 1. By this way we go on repeat, and this is a multivariate one point iteration. So, in mathematically x at j plus 1 is equated to x at j by some function g, that is why it is called multivariate one point iteration, and repeat this process until you have two conditions, either you specify maximum number of iteration or you specify some convergence limit. We learnt about convergence limit, that is one such criteria under the convergence limit. For example, if the difference between present value and old value, take the absolute and you specify some limit, if that absolute value of the difference is less than the specified value, then you can terminate the iteration. This is one such convergence criteria. So, you repeat this procedure, either specifying convergence criteria or you forcibly say we will do the iteration only for a fixed number of iteration, say 500, 1000, whatever be the error accumulation. Slowly as the calculation proceeds, that will also come down. So, let us start with the list of linear equations as we did before, a11 x 1 plus a12 x 2 plus a13 x 3 all the way, and then b1 on the right side. Similarly, for all the rows we get last row a n 1 x 1 all the way up to a n n x n equal to b n. Now, what do? We start with the initial guess value. So, x 1 is to be determined, and all other terms on the equations are brought to the right side as shown here. Now, in this values for x 2, x 3 all the way up to x n are from the guess value or from the previous iterated value. So, you get approximately values for x 1. Now, we go to x 2 and all the way up to x n. We will explain different iterative procedure by taking one example problem, and that is shown here as a 2D Laplace equation dou squared u by dou x squared plus dou squared u by dou y squared equal to 0, and this is a elliptic equation. If that example equation that we have taken is discretized using second order accurate central differential scheme, then we get finite differenced form of that equation, and that is shown here. So, let me read that term: u I plus 1 j n minus 2 u I j n plus u I minus 1 j n divided by delta x squared. So, this is a central differential scheme which is applied to the first term in this equation dou squared u by dou x squared, and we use two subscript, one I for x, second j for y, and as usual superscript n is used here for iteration level. We write a similar term for the second derivative in the y direction, and that is what is shown here. Now, j is given index j plus 1, j and j minus 1. A corresponding computational molecule is shown here. So, I and j is a point of interest, and we consider values from neighbors I minus 1 comma j, I plus 1 comma j in the x direction. Similarly, in the y direction you have I j plus 1 and I j minus 1. So, these 4 neighboring nodes contributes for the solution at node I comma j. For the example problem, the computational domain with the mesh arrangement is shown. Delta x and delta y are the respective spatial difference between two mesh points in x direction as well as in y direction, and we define a new term beta which is equal to delta x by delta y, and we apply boundary condition along x as well as along y. With the specific of nodal points, the same computational domain is repeated here. So, 1 comma 1, 2 comma 1, 3 comma 1, 4 comma 1, 5 comma 1 for example is along the first row for first in y direction. Then we extend this for the remaining nodes, and it is marked here. We define another term alpha equal to minus 2 1 plus beta squared. Now, we apply the discretized equation what we had before, what we have written before, that is second order central differential scheme for dou squared u by dou x squared, dou squared u by dou y squared. Use this definition of alpha and beta. For this mesh arrangement, you apply for each nodal point. For example, 1 comma 1, 2 comma 1, this may be coming along the boundary, or you take the second row. So, 1 comma 2 is again on the left side boundary, 5 comma 2 is again near the right side boundary. So, if apply for example, for the node 2 comma 2 discretized equation, then we get the first equation as shown here. So, 2 comma 2 node is influenced by neighboring nodes, that is 1 comma 2, 3 comma 2, 2 comma 1 and 2 comma 3. They are respectively I minus 1 j, I plus 1 j, I j plus 1 and I j minus 1. So, you get corresponding equation written here. We extend this procedure for all the nodes. So, it is 2 comma 2 is here, 3 comma 2 and 4 comma 2. In the same way, equations are written for all the nodal points. Now, if you put all those equations in the form of a matrix, and you get a structure as shown here. Now, in this alpha we have already defined, beta also we have defined. Those alpha and beta are definitions are for convenience, so that discretized equation and the matrix are written elegantly. If you look at in this matrix, then along the diagonal you have alpha, then immediately above super diagonal, immediately below subdiagonal, then there are two zeros entry, then you have beta squared that is also appearing parallel to the diagonal on the upper side as well as on the lower side. So, this is like one form of a sparse matrix, and all the unknown u vector are given, then known coefficient value is given on the right side. We will explain different iterative procedure for that matrix and that example problem. First one is a Jacobi iteration method. In this, the equations are solved using initial guessed values of the neighboring points or from previously computed values. So, that finite difference equation, it becomes as shown here, the node of interest, that is u I comma j, current iteration value superscript is n plus 1. So, u I comma j n plus 1 is the one that to be determined at the node of interest I comma j, and all the neighboring nodes are taken to the right side. They are either determined from the previous level or known from the guess value, and that is again molecule. So, we have the rewritten form of that discretized equation when you follow Jacobi iteration method. The next one is a point Gauss-Seidel iteration method. In this method, the current values of the dependent variable are used as soon as they are immediately available. So, the discretized form is written for point Gauss-Seidel iteration as shown here. Though it looks similar, you have to pay attention to a particular term, that is u I minus 1 j with a superscript n plus 1 and u I j minus 1 with a superscript n plus 1. So, in the computational molecule, if you look at I comma j is a point of interest, u I minus 1 is on the left side and u I j minus 1 is at the bottom. Values at these two nodes are known from just immediately completed iteration procedure. So, they can be immediately used because they are available. That way, the nodal value I comma j is more realistic, because we learned from this discretization procedure I comma j value is influenced by neighboring nodes. So, if you take very close value, then the solution can be obtained faster, and in this procedure values at node I minus 1 comma j and I j minus 1 are known from just completed iteration. So, why not use it, and that is the idea of point Gauss-Seidel iteration method, and we are going from point to point, that is why the word point is used. So, discretized equation written for point Gauss-Seidel iteration procedure has values immediately found included. That is why you see the superscript n plus 1 for left side node as well as node at the bottom. Next is a line Gauss-Seidel method. In this method, the finite difference equation is rewritten with the unknown points at I minus 1 j, I comma j and I plus 1 j, and you can see the equation here. So, I minus 1 j, then we define 1 plus beta squared I comma j, then u at I plus 1 j n plus 1 equal to values known at j plus 1 and j minus 1. Here this is along the line, because I minus 1 is on the left side, I comma j is a point of interest and I plus 1 is on the right side. So, we identify nodes along that particular line and they all have to be inverted together, and that is the idea behind line Gauss-Seidel method. If we extend this procedure for all I at particular j, then it will result in what is a system of linear equation, and it will have finally a tridiagonal matrix form. Because if you look at this equation again, I comma j is a point of interest and you have one on the left side, one on the right side, and you extend this for all I and j for a particular j, then it will result in tridiagonal matrix form, and we learned TDMA procedure in the previous class. Now, this step is repeated for the next line and you finally get one full matrix. Though individually it appears to be taking more computational time per iteration. The convergence rate is faster than that is required for Gauss-Seidel method. Graphically, the line iteration procedure is shown. So, initially you have values along this particular j node not known, previously iterated values are shown by the triangle, or from the previous known previous time level or previous iterated values are shown again with a triangle. So, along this particular j and you set up equation, when you solve equation for that particular j, then this nodes values are coming to known and they are used for the next level as shown here. So, now for the same line j, it becomes triangle, that means it is a known value, this triangle becomes unknown value along the same j, and then we have previously iterated value just above. So, this way you repeat this procedure and you get complete solution. Next we see a procedure called point successive over relaxation method, otherwise PSOR. So, we know the solution is progressing and it is likely to reach the solution in the same direction, and this is what is known as a directional change. So, if a trend is observed, why not we accelerate, and that is the idea, and that is implemented by a procedure called over relaxation method. So, u I comma j n plus 1 is to be determined. We now introduce a factor called omega and 1 minus omega. So, this is a kind of a fraction. So, omega is 1, then the contribution of u I comma j n is actually 0. If omega is less than 1, say for example 0.2, then it becomes 0.8, 1 minus omega becomes 0.8. So, we take 80% weightage of previous level value for the same node I comma j, that is the meaning of the term 1 minus omega u I comma j n, and the remaining terms again we introduce omega for taking the weightage of neighboring nodes. If the relaxation parameter omega is equal to 1, then it will result in Gauss-Seidel method, which we have just now seen. If the omega has a value between 0 and 1, the method is called under relaxation method. If it is above 1, then the method is called over relaxation method. Now, what is shown here is only a sample example equation. You can write this for auxiliary equation as well, and you need to define omega differently for different equation, because different variables will behave differently when you iterate. Next is a line successive over relaxation method. This is same as PSOR, only thing it is implemented for the line as a whole. So, we have omega I minus 1 j n plus 1 value, then for I plus 1 etcetera, and similarly for neighboring nodes contribution. There is another procedure what is known as the alternating direction implicit ADI method. In this method, we go from nth level to n plus 1 level in 2 steps, that is n to n plus half and then n plus half to n plus 1. Now, every time one set is given in implicit, another set is given in explicit. The first step, for example, it is implicit in x direction and explicit in y direction. Accordingly, you can rewrite the discretized equation. So, we get final discretized equation as shown here. The next stage, n plus half value is known and it is explicit in x direction. So, it is taken to the other side, and implicit in y direction, that is taken on the left side. And we already learned this is usually applied for pentadiagonal matrix, and by applying this ADI procedure it gets reduced into tridiagonal matrix, and it is possible to apply TDMA procedure to get solution. It is also possible to introduce a relaxation parameter as we did in SOR procedure and accelerate the solution. Now, ADA method is explained graphically as shown here. So, value at n plus half you do sweep in x direction and n plus 1 you do sweep in y direction. So, in this class we have seen in detail particularly iterative methods. To explain different procedure, we took an example problem, that is Laplace equation. We discretized by second order scheme, and we explained different iterative procedure for that example problem. We understood advantages. We also learned method of reaching faster by a procedure called over relaxation or under relaxation. Thank you.